All right, so today we're going to review inverse functions. So if you remember anything about an inverse from previous years, an inverse will undo a given relation. Okay, and this is the most important thing right here. Every inverse relation can be found by switching each x and y value. So your domain becomes the range, and the range becomes the domain from a function to its inverse. All right, so here we're going to find the inverse relation. So in this first little table, we have x's and y's given to us. If we exchange those for each other, then we'll have the inverse. So this one's going to be the inverse. That means for this first point, 1, -1 is now -1, 1. 3, 2 becomes 2, 3. 4, 0 becomes 0, 4. And 6, 2 becomes 2, 6. So in the original table, if you remember, we're deciding if it's a function or not. And it is a function because every x has only one y value. So this is a function because each x has exactly one y. Now, the inverse, however, is not a function because if you notice, the x value of 2 has two different y values, 3 and 6. So it would not make it a function. Every x has only one y value for it to be a function. Now, this is going to be something we will talk about a lot. If the inverse is not a function, that tells us the original, in this case it was a function, was not invertible. And we'll elaborate more on that later. But invertible just means that the inverse is a function. And in this case it wasn't, so it's not invertible. All right, next example. We're sketching the inverse. So if we're dealing with an inverse, we're going to switch x and y. So let's talk about the original. What points do we have on the original? So first one, we've got -2, -1. This next point is -1, 2, 2, 1, and 4, 3. So now if we want to sketch the inverse, we want to switch those. We want to sketch -1, -2. And we want to plot 2, -1. Then we've got 1, 2. And lastly, 3, 4. So this is the inverse. All right, now if you notice, is the original relation a function? So look at the one that was given to us. Is the original one a function? And that is yes. The original is a function because every x has only one y. Okay, every single x has its own y, has only one y. All right, let's talk about the inverse. So is the inverse a function? And that would be a no. So the inverse is not a function because that's really messy. All right, now if you have a graph, remember you can check by doing the vertical line test. You can't use that as your reason now. We're in pre-calc AP, but we can say because every x does not have only one y value. And it's nice to give an example of where, and anywhere between 1 and 2. Let me erase this. Let me highlight it. Anywhere in here, we actually have multiple y values for given x's. So between 1 and 2. Okay, so if you notice here in this graph, it says graphical property of inverses. The graphs of inverses are really just reflections of each other over the line y equals x. If I put that line in here, this would be y equals x, and we could fold those right on top of each other. Okay, they are reflections over the line y equals x. So that's a nice little thing to note there and pay attention to. All right, now the invertible piece. A function is increasing, decreasing only, then it is invertible, meaning the inverse is a function. If it turns, has any maxes or minimums, is no longer invertible because you'll have output values that are the same for different input values, meaning every x won't have its own y. So it says think of using the horizontal line test to test if a function is, remember that last year we went over that it was 1 to 1, but it also tells us if our function is invertible, meaning its inverse is going to be a function. The vertical line test to see if it's a function, horizontal line test to see if it's 1 to 1, or if its inverse is a function. Okay, so some important information there that you want to make sure you know. So are the following functions invertible? What you would do, visually check to see if it's passes the horizontal line test. You cannot use it as a reason, but that is what you think and that's what you do. So here, this would pass the vertical line test. So yes, g of x is invertible. And then it wants us to sketch the inverse. So let's see, we got the point -1, -4. I'm sorry, -3, -4. So we're going to go -4, -3. I'm going to plot this point, which is at -2, -1. So -1, -2. It's going to kind of come this way. Let's do this y-intercept. Somewhere between 0 and -1. So I'll put that here. Looks like we had an x-intercept around 1. So 1, 0. So I'll do 0, 1. And then 2, 3. So 3, 2. All right, looks pretty good. Okay, you just want to kind of get enough. I wouldn't just do the endpoints and then try to wing it. Try to get a few more that are kind of on there clearly so that you can get the shape of it. Look, nice reflection over that line, y equals x. All right, let's do the next one. All right, so this one clearly would not be invertible because it fails the horizontal line test. So okay. And we'll give a reason here because as each x of g does not correspond to an unique or different y value, so the inverse will not, will not have each x going to only one y. All right, so we're going to sketch this one. What do we got? -4, -2, so -2, -4. Let's get this point, -2, 1, so 1, -2. To this vertex up here, -1, 2, so 2, -1. And then y-intercept somewhere between 0 and 1, so then between 0 and 1. Let's let's get this point. It's around 1, -1. And then 3, 3. Okay, looks pretty good. All right, so something to note because we're switching everything, and I said this in the beginning, the domain and range of a function and its inverse are swapped with one another. So when we look at a function, we can find the minimum value, nice and easy. Minimum value here would be -3. What would be the minimum value of the inverse? This is your inverse notation. So if we look at the domain of f here, the domain is from -2 to 3. That is going to become the range of the inverse. Let me use my notation. So if the domain has a minimum of -2, that means the range of the inverse is going to have a minimum of -2. Okay, so it should be the minimum of the inverse. All right, if we want to find an inverse, switch x and y. So steps over here in this box, but you've done this before. Switch the x and y values. So we're going to go x equals 3y minus 7, and then solve for y and get it by itself. So we can add 7 over, divide by 3. Because this is a line, that means it's going to be a function. So I'm going to go back and use inverse function notation. And it doesn't matter how you write it. You can go x plus 7 over 3. You can break it up and do 1/3 x plus 7/3. Okay, but if the inverse is a function, you should use your function notation. All right, now we can find inverses of all sorts of functions. The hardest ones usually are rational functions. So just some steps. You did this last year in Algebra 2, but we'll review it here. So switch our x and y values. So let's do that here for this first one. X equals y minus 2 over y plus 3. And it says multiply and distribute both sides by the denominator. Okay, so we're going to multiply by y plus 3 on both sides. When I do that on the right, that cancels out. So I just get y minus 2. And on the left, we're going to distribute. So xy plus 3x. Now we're solving for y. So move all terms that include the variable y to the left side and move anything that doesn't to the right side. So I'm going to subtract y over and subtract 3x over the other side. Notice I can't combine those y's because one has an x, one does not. They're not like terms. All right, now factor out the y. So it's GCF here. So I have x minus 1 when I factor out y. And then lastly, if I want y by itself, I can divide by x minus 1. It's another rational function, so make sure you use your notation. There's our inverse function. Okay, so all steps that you are fully capable of. Let's do it again just so we get the feel for it. So let's switch our x and y. All right, let's get rid of the denominator, so multiply both sides by it. Now let's get y to one side, so we'll subtract it to the left, and I'm going to add the 3x to the right. Factor out the y, and then divide both sides by it. There we go. All right, and then lastly here, if we have two functions that are inverses of one another, so g of x is equal to the function of the inverse of function f, that means xy is a point on the graph of f, yx is a point on the graph of g of x. True. The domain and range of each other switch. Okay, so that's true. And so just a little recap of everything. A continuous function will only have an inverse function if it is strictly increasing or decreasing. If there's any changes from increasing to decreasing, it will not pass the horizontal line test. Thus, the inverse will not be a function. Okay, so what do inverses actually do? So we're going to talk a little bit about evaluating here. If you plug a number into a function, it generally will output a new different number. So if we plug x equals 2 into the function f of x equals 3x minus 1, we get 5. Okay, that's great. Now, if we plug the answer 5 into the inverse function, the answer should actually be the original input, because what we just showed was on f, we have the point 2, 5. If we switch to the inverse, we should have the point 5, 2, right? So the input on the function will give us an output. If I take that and put that back in the inverse, I should get back to the original input. Okay, because an inverse undoes a function. So if we plug in x into a function, we get an output. If we plug that output back in, we should get x again. So that comes down to this last little idea we're going to deal with. If two functions g and f are inverses of each other, if and only if f of g of x equals x and g of f of x equals x, that means you're plugging them into one another and they're undoing it and you're getting back that x. Okay, to show that two functions are inverses, we must show that the compositions of both come out and equal x. Some function composition here. So let f and g be functions, determine if they are inverses. So we're going to start by doing f of g of x. That means we're doing f of 1/2 x plus 3/2. So this all gets put into that x here. So it's going to be 2 times 1/2 x plus 3/2 minus 3. Distribute. That would be x plus 3 minus 3. 3's will cancel each other out. F of g of x equals x. And now similarly, let's do the same thing for g of f of x. So all your work should be labeled. It should be clear. We should be able to follow it. Don't skip too many steps. So f of x is 2x minus 3. That's going to go into g. So now it's 1/2 times that quantity plus 3/2. We're going to distribute. So x minus 3/2 plus 3/2. Those 3/2 will cancel. G of f of x equals x. So since you have to write something, since f of g of x equals g of f of x, and they both equal x, f and g are inverses of one another. Now, there might be times where we have to restrict a domain to ensure that the two functions actually end up being inverses of one another. So let's talk about that. Okay, now first example here says h of x is x squared plus 10. What we know about h of x is that's a quadratic, not one-to-one, so its inverse wouldn't be a function. But if we restrict it to where x is greater than or equal to 10, then they will be. So that's a good thing. So let's check to see if these are inverses of one another. So we do h of k of x, means we do h of the radical function. So radical squared plus 10. We get just the radicand. So that equals x. Do the same thing just the other direction. So k of h of x. So k of x squared plus 10, which means that's going into here. So x squared plus 10 minus 10. 10's cancel, and the square root of x squared is x. So h of k of x equals k of h of x, which equals x. So k and h are inverses. All right, we'll work more on that tomorrow.